Okay, so I think now it's recorded. Normally, yes.
Yes.
Okay.
Bon, bah écoute.
Okay, so good afternoon, everybody. Last week, we talked about some regression problems for compositional data. And today we are going to see some applications in ecology, especially with abundance data. So we will briefly define what is abundance in ecology, of course. And then we will see that the main difference with this problem is that we'll have some dynamic in our problem. So obviously we will study time series model. So just I will share first my screen and no, this is not the correct one. Sorry, there was just one thing and it's not good. So I think partager. It was not the correct one, sorry. Présentation. Non, c'est bon.
C'est ça quand même.
Yes, but I was. No, these are just my notes, but this is not. Stop sharing. Okay, partager, share. It's always it's not the correct one.
Sorry.
C'est toujours celui-là qui me propose, mais c'est pas du tout ça que je veux.
Ah, attends. Il ne doit pas être ouvert l'autre.
Okay, il est là. Okay, so the question is, does everybody see my screen?
Refais le partage. Non, non, pas du tout.
Okay, so
il faut refaire le partage. Il faut refaire le partage.
J'ai sur Zoom.
Hop là, et là on peut
partager. Aperçu. Okay. No, it's good. It's okay. Présentation.
Il faudrait remettre en.
Okay. So we are going to talk about abundance data. Okay. Okay. So first of all, the abundance in the ecology, it's a very central and crucial question because it's a measure of the commonness and rarity of species. And first of all, it's also a measure of the wellness of the species in a given ecosystem. There are two ways to define the abundance. The first one, I think it's a very easy one, is to say that the abundance is just the total number of individuals. Okay, there's someone who has a question maybe or no? I don't know. Okay, so this is just the standard abundance. I have an ecosystem with a certain number of species and a certain number of individuals, and I'm counting the number of zebras or lions, I don't know. This is just count. And there is also the relative abundance of a species. And here it's just the proportion of each given species in the ecosystem. Okay, so it's a proportion among all the individuals of all the species in the ecosystem. So standard abundance has been a lot studied in the literature because it's a good measure for the commonness or rarity of a species. If you have a big number for the standard abundance, it means that you have a lot of individuals for this species, so it's a very common species, for example. So it's a measure of the wellness of a species. However, the relative abundance is also something very interesting because here you don't have the total number. You don't know if you have a lot of individuals. But since you have all the proportions, it's a good measure for the biodiversity. For example, if you have in an ecosystem 90 5% of a species for the abundance, it means that you have almost no biodiversity. Like something really stupid, if you have three species, A, B, and C, if your relative abundance is given by this vector, so 0, 95, 0, 0, 2, and 0, 0, 3, you don't have any biodiversity. Ah. Ouais, c'est juste ça, je pense que ça va aller. So relative abundance is something that is that has a lot of importance. And because we are studying proportion of the individuals of the species, we have a problem with, so here I have an example. We have a problem with compositional data. Okay, if you have everything with a, here you have a very childish example. Everything in percentage, you can choose to just take the proportion. So you have data on the simplex. Here, for example, the first line vector is a vector for standard abundance, and the second one is a vector for relative abundance. Okay, so we have some data on the simplex. Yeah, I will just remind you that the simplex is the set of the vectors in RD with all the components between 0 and 1, and the components must sum up to 1. Okay, what else they want to say about abundance? I think it's the most part of it. Now I'll just explain to you our general framework for the models we will use. So I will never talk about standard abundance. I really focus today on the relative abundance. And obviously, the abundance of a species can be explained by a multitude of exogenous variables. You can have the climatic variables, for example, the temperature, or the precipitation, or a lot of other things. You can also have the pollution. Okay, if you have a lot of industry in some country, maybe some species of birds or other animals or plants will decline. So, because we have several variables that can explain the abundance, we have a problem of regression for compositional data. But there are also other explanations, because obviously the abundance, obviously for me, I think, the abundance of one species is affected by the abundance of the other species. If you take the childish example in the savannah with the lions and zebras and other things, if you have a lot of lions, maybe you won't have a lot of zebras for some time. But if the lions don't have anything to eat, then they will die, and maybe we'll have also a lot of zebras, for example. So it's kind of a Lotka-Volterra equation. But the idea is that you can guess that abundance of a species has a certain dynamic. Okay, so it will move along the time, and it's not a regression problem that is static like last week. So what we want to do is to have a nice model to explain the dynamic of the abundance along the time. So we will work with time series that we will be vectors of abundance. And in order to simplify the things, we will not take into account impact of exogenous variables, such as pollution or climatic variables. We will just focus on a vector of abundance. So the only explanatory variables of the abundance are the the past value of abundance. Okay, so our time series will be denoted YT. Okay, so we have these species in our ecosystem. And YT is the vector of abundance. It's a vector in the simplex. And I will denote with a little yt a realization of the random variable big YT. So it's the abundance at time t. So we will assume that we have a big sample of abundance. We have a sample of size big N. And just to take a little look at an example, here we will work with, especially with a data set of birds. So here we have a large data set from 1964 to 2001. It's not that big, I know, but imagine that there was a scientific that every year recorded the population of birds from 1964 to 2001. It's quite long, actually. So here we have 3 species of birds, Antus, Calcareus, and Unant. These are some really small birds in Scandinavia. And we have the vectors of relative abundance. So you can immediately see that the first species, Antus, is really a big part of the ecosystem. Okay, so we have this kind of data set. And the goal is to find a model to explain the dynamic of our abundance. Okay, here at first sight, we have the impression that the second species is somehow taking the power because it's growing every year. And the species Antus is a very small decline. Yeah, in abundance. Okay, and just to have another representation of our data, here we have the 3 abundances, 3 relative abundances of those species from 1964 to 2001. Okay, so there is something, we say, some phenomena that are quite strange. For example, in 1970, you can see that the species Calcareus has a huge evolution, okay, at the expense of the first one, Antus. And also during the 90s, there are a lot of strange data, okay, because there are a lot of variability in the species Calcareus. So that's quite strange. And we will see later that, okay, maybe something happened during those, also this period is quite strange. There was probably something that can explain those variability because the model is not behaving very well at this period. Okay, so like the other day, we have 2 main strategies that are data transformation and the stay in the simplex approach. So it's always quite the same idea. I will go maybe faster than last week. With data transformation, the idea is to take a value of abundance and apply the additive log ratio transform. Okay. So this is a one-to-one mapping, and we with our vector z here on the right side. The vector z is not in the simplex, but in RD-1. So we have no constraint on it, and we are able to apply any kind of regression on the transform data. So we denote the transform time series ZT. So I recall that YT is the time series of abundance. So ZT is the time series of the transformed abundance. I use the ALR transformation, okay, for the additive log ratio. So because with our species, YT was with our bird species yt was a vector with 3 components, zt will be a vector with 2 components. Okay, and if I just, okay, so this is not really important. Oh, I thought, okay, I thought I was, I had a plot, but apparently not. Sorry. Okay, just remind you, okay, just don't forget that zt is a vector in R2. Okay, and just like the other day, we can then, if we have some fitted values on Z, on the transform scale, it is possible to have fitted values on the original scale with the inverse transform of the function ALR that is given here. Okay, for time series ZT or value Z, it's possible to obtain the original data with this inverse transform. And it's quite easy to calculate. So this is the first strategy, but now that we have transformed our data in a time series ZT, which model could we choose? So here I will just propose the very easy Var model. So Var is for a vectorial autoregressive model. I don't know if everybody had the opportunity to work with some Var models before, or maybe not. Okay. So I will just present it very quickly, but you will see that it's a quite easy model. In theory, it's not that easy to prove the good result, but it's quite easy to understand. Okay, so the principle here is that we will assume that at a given time t, zt will depend on the past values of itself. Okay, so at time t, the transform abundance, the time series z here, it will depend on z t minus 1, z t minus 2, etc., etc. And we have a like value of p. So p is still to be determined. Okay, so zt is just a linear combination of the past value. We had a constant c and a Gaussian white noise. So here, the process epsilon t, which is a Gaussian white noise. So every epsilon t is a Gaussian vector. And we assume that those variables epsilon t are independent. Okay, so these linear combinations, phi I are matrices, okay, because we have vectors for z. And the idea is just, okay, remember just that the idea is that we assume that the transform abundance at time t will rely only on the p last value of the transform abundance. And we have maybe some noise because there is some variability. It's not exactly perfect. Yes, just some important results about Var models is that under some assumptions, okay, here if we consider this this complex matrix phi of z, which is the identity minus the sum of the z at the power j phi j. Remember that phi j are the matrices in the Var model. If all the solutions of this equation has an absolute value that is larger than 1 and strictly larger than 1, then we will have one and only one stationary process that is that satisfies the equation just above. Okay, so it's equation, I don't have a number, this one. Okay. So if the determinant of phi z equals 0 implies that the absolute value of z is greater than 1, then we will have one and only one stationary process for our model. Okay, it was there. So here I just wanted to show you the transformed time series, Z1 and Z2. And we will assume that this time series, this multivariate time series, will follow a Var model, just the one we presented before. So here we have the partial autocorrelation functions. Okay, so the partial autocorrelation function, it's the correlation between ZT and ZT minus K, but without the intermediate values of abundance. Okay, maybe I will just stop sharing because I will write something on the board. Okay, so now you should see the board. Okay, because on the presentation, I talked about the partial autocorrelation. I think I will also just switch on the lights. That's what. That I will call PSEF. If you want, just the idea is that it is a correlation between xt and xt minus k, but without the impact on if we don't take into account the variables xt minus 1, xt minus 2, xt minus k plus 1. It's just, so it's not mathematical at all here, it's just the idea. Okay. There is a mathematical meaning in terms of projection, of course, but yeah, just if I want to make it simple, just if you have never seen that, the PACF is a correlation between those two variables. Just the global idea with no mathematics at all here. Just remind that. Okay, and in a Var model, well, you have a result that is in case of k is equal to 0. When k is greater than p, normally. Normally, if we chose the right model, we must observe this, this equation in our empirical PSEFs. So, okay, we just share the presentation again. No, it's always not the right one. À chaque fois, il me remet là-dessus, c'est agaçant. C'est épuisant. Celui-là, je peux le fermer en fait, celui-là. Ça, je m'en fiche. Attention, parce que du coup, tu vas avoir ta boîte mail.
Non, mais ça, on s'en fout. Mais non, là, on était là.
Ok, c'est bon, merci.
Est-ce que ça marche?
Ouais.
Ah, mais attends, là, c'est pas encore.
Si, c'est partagé.
C'est partagé, d'accord. C'est partagé.
Okay, so if we take a look at our partial autocorrelations, here in blue, the dotted blue line is just the level of significance, yes?
I don't understand why the partial autocorrelation factor doesn't depend of T.
Oh yeah, because we assume that our process is stationary, so it won't depend on. Okay, and it's possible if the equation with the determinant of phi of z is equal to 0, with implies that the absolute value of z is greater than 1. This is a condition. If this condition is satisfied, then our process will be stationary. We have at least one, and we have only one process that is stationary. And we will assume that we are in this case. So yes, it won't depend on T. It won't depend on T. But that is not obvious at first sight. I agree. So here, if this is correct, so we have the different values of the PSCF functions. And okay, so here it's always 0 because it's never significant. And for the other ones, okay, for the first one, it's for the series Z1, we could guess that P is at maximum 3, let's say. For the third graphics, the one on the bottom left, it's not very clear that we have a Var P model, okay, because there are several like values for the PSCFs that are significant. And for the fourth autocorrelogram, you can see that there is just one value that is significant, maybe.
But sorry, what is the partial correlation of Z1 and Z2? The partial correlation between Z1 and Z2?
Well, here the PSCF functions actually are matrices.
No, because if Z1 is not the partial correlation of the series Z1, the vector. What is Z1 and Z2 together? Is
actually here, imagine that it's a way to represent a covariance matrix.
Yeah.
Because PSCF of K, actually, I said correlation, but since we have vectors, these are matrices. PSCF of K, it's a matrix. Here it's a 2 by 2 matrix.
Okay.
So here it's a variance of Z1 T and Z1. No, it's just variance of Z1 T. Here it's the variance of Z2. So Z2 is just
another should be symmetric mathematics.
There's a doubt here.
That was just because of the difference between these two.
Yeah. These are not the same, and you expect it to be symmetric.
Yeah.
Maybe I just. You have a doubt? No.
This for the same sample.
Yes. That's strange. I did not notice it before, but yes, it's strange. Maybe I made a mistake in my in my command in R. Yes. Okay. Maybe I made a mistake, or I did not print the correct graph because that's strange. Yes, that's very strange. Maybe it's not the correct one. Well, what I wanted to say is that I decided to take a Var 3 model. I took P is equal to 3 in my model, just to see what it would give. And So the values of the different matrices phi I, so phi 1, phi 2, phi 3 are computed by maximum likelihood estimator. And here in this graphic, you have with the full line the real values of the three abundances, and in the dotted lines are the fixed values. So with a Var model. So obviously for the three first values, they are the same because we always need three past values. And after it starts to be a little different. Yeah, but the Var model is, has some nice fitted values. So note that at each time, I rely on the three past values, but the three true past values. Okay. So it's like if I made a prevision, but at step 1 with an horizon equal to 1. For example, in 1980, I have the three past values, and I'm just wondering, okay, what is going to be the abundance in 1981, etc., etc. So I just have an horizon of 1 year. But okay, still the fitted values are pretty good. Just an illustration of the data transformation approach. What can be interested is the stay in the simplex approach. Okay, so there are some mathematical tools that I will explain before getting back to the model at the end. So just like last week, we will use a directed distribution. Yes.
Can you just come back to I don't understand if the values we calculate are calculated with all the data or all the previous data.
It's just the previous data. Well, it's all the data, but I would say they are calculated step by step, okay, in some way. Okay, I know the three first values, and for the first one, I use the three true past values, and I make a prediction, which is here, for example, okay, here, here, and here. And I do it again, but with the three true past values. Okay. I don't use the approximation I made, which is also why I have such a nice fit. Because if I wanted to use the estimated value as a true value, if you want, I won't have something that is so close to the reality.
So you saw set P equal to 3 in this opinion.
Yes. Yeah, yes. You could try with another value of P. But it was
determined by these
yes,
correlograms.
yes, but it's just determined by by a visual inspection of the autocorrelograms. So here maybe it's not the correct one, so I will have to check that. But you have something with the logic software R, you have something like that, and you should see that okay, the like values, the PSEFs are not significant after 3. So okay, you can try with 3. It's not.
Sometimes correlograms are not a good way. You can also use the KK criteria for the
Yes, there are multiple, but I did not want to, because that's not really the model I want to build. Yeah. So I just made it really quick. So with just a visual inspection. Yeah. Okay, so it's okay. So you see how it's calculated. So yeah, with the stay in the simplex approach, we will use like last time the Dirichlet distribution. But first, I would like to remind or to explain some properties about Markov chains and ergodicity that are really crucial here. Okay, so this time we will assume that the abundance Y will follow a directed distribution. Okay, where X is vector of explanatory variables. So here, what you see on the slides is the model we used last week. Here we do not have a vector of explanatory variable X. X are just the path values of our process. So what we will truly have for our model is that the random variable YT will follow a directed distribution with mean mu t that satisfies all these equations for I between 1 and d minus 1. For I is equal to d is just 1 minus all the other means. Okay, so here you have some kind of multinomial logistic function for the link between mean mu t and the path value y t minus 1. All the vectors beta a are unknown, and we will try to estimate them. And we also have a dispersion parameter for the directed distribution that is called phi, and it is assumed constant here in the first place. So in my model, the mean of the abundance at time t will only depend on the last value of the abundance. Okay, but it is also possible to use some other path values. Okay, so I just took yt minus 1 as a covariate, but you can take several lag values, yt minus 2, yt minus 3. There is no problem at all. But I wanted to keep it simple, so I will just, for now, assume that our model will satisfy this equation. So we will see that our model will, in the end, will be a Markov chain. So I will just recall some definitions. First of all, is the transition kernel. So just assume that we have two measurable spaces E and F with the sigma algebras big E and big F, that's calligraphic E and calligraphic F. An application K defined on E times calligraphic F and valued in the interval 0, 1. We say that it is a transition kernel if for all x, the application kx of a measurable set is a probability measure, and if for all event b in f, the application that will take some value of x, and here b is fixed, is measurable. Okay, so if I fix the value of x, we have a probability measure, and if I fix some event b here, we have a measurable application. So this is a transition kernel. It's also called the Markovian kernel sometimes. And the Markov chain, well, it is just a stochastic process yt that is valued in the measurable space E. And we will denote ft with a minus sign. Here it's the sigma algebra generated by all the path values of the process Y. And ft is just the sigma algebra generated by the random variable at time t. And so our process is the Markov chain. If for any measurable bounded function, we have the conditional expectancy of f of yt conditionally to the sigma algebra of the past is just equal to the conditional expectancy, but conditionally to just the last sigma algebra. So these are just the equations, but intuitively, the idea is just that with the Markov chain, if you know the entire history, if you know the entire past of the process, you won't have more information than just knowing the last value. Okay, just keep that in mind. But in a mathematical way to say it, it's just there. If you take the conditional expectancy conditionally to all the past, it's just the same thing that conditionally with just the last sigma algebra. So here we will denote the transition kernel K. Did I talk about? I don't remember. Because I said many things, but okay.
I guess subindex and superindex are the same.
Yes, it's an error that I made. Actually, I just wanted to make such the above index, not the sub-index. All the t are above normally, but it's all the indices are the same normally. Okay, so we will say that a Markov chain YT will have a transition kernel K if we have this relation. So the conditional law of YT, so conditionally on the last value, is the kernel K evaluated on YT minus 1 and A. Here you can see that the transition kernel K does not depend on the time t, because we will assume that the chain is time homogeneous. It's not always the case, but here we will assume that the transition kernel will not depend on the time variable t. It just depends on the last value yt minus 1. It's just a definition of the transition kernel K. So here our transition kernel is the conditional law of yt depending on yt minus 1. So I know that you talked before, when it was 2 or 3 weeks ago, you talked about ergodicity. So just some reminders about ergodicity that will be essential in our future work. So I just wanted to recall here the shift operator. It's not sigma, it's tau. Oh, that's sigma. Shift operator is not sigma, it's tau. Okay, so if you take a sequence yt, tau of yt is just the sequence yt plus 1. Okay, and here in our framework, we also choose a stationary process yt of law of distribution py. So py is the distribution of all the processes here. And it is said ergodic if for all tau invariant event A, the probability of that y is belonging to A is equal to 0 or 1. So such an invariant event will occur almost surely or never. Almost never. I think you talked about ergodicity before, but just a small reminder. And here the interest of ergodicity is that we will be able to establish a strong law of large numbers. Okay. So here actually, if you take a function g defined on the space E and valued in R, such that the expectancy of the absolute value of g of y0 is finite, and the process is ergodic. Okay, yes, I wrote it. So if the process yt is ergodic, then you will have a strong law of large numbers. Okay, that is really important here, this last equality, because when we will want to estimate the values of the betas and the dispersion parameter phi in our model, it will guarantee us that the maximum likelihood estimates are strongly consistent. Okay, so ergodicity here is really crucial because without this notion, we won't be able to have good estimates. So of course,
est-ce que c'est clair la différence pour vous entre les deux équations? Dans la première équation, la fonction est définie sur l'ensemble des suites.
Yes. But maybe just if you remember just that, it's more clear, I think. I think it's more easy to understand this one.
For sure.
But yes, here you have a function that is defined on the sequences, on the entire sequence of yt. And here g is just defined on E. Okay. F is defined on E power Z. Here it's just defined on E. Okay, so the most important part here of ergodicity is that we will have a strong law of large numbers.
Of the sample mean no.
If you want to have the convergence of sample mean and yes.
So it's implied.
Yes.
Oh.
Yes, but it will be it will be
Also,
more
yeah.
useful with for the log likelihood, of course. Here, actually, g will be a function of will be the log likelihood in our model.
Okay.
And
So at the moment,
could be the moment, but the big interest in our model is that g will be replaced with a log likelihood function. And with some additional hypotheses, we will have the consistency of the estimators. And I think it's also important for, but I don't really remember, I think yes. It's important for the asymptotic normality also.
yeah, because G is would be at the moment of the distribution, then you have also the
Yes.
centrality theorem. No?
It could be, yes. Yeah.
Score and call, yeah.
Okay, one or two other definitions. If you take a transition kernel, okay, so remember that it's kind of an application that is both a probability measure and a measurable application. We said that the probability pi is k invariant if we have pi times k is equal to pi. So pi times k is defined just here. So it's which is the integral of k y a with the measure pi. Okay, so if this integral is equal to pi of a, we say that pi is k invariant. And it will be quite important, actually, because there is a theorem that it's not that difficult, but it's quite long. That if a transition kernel has one and only one invariant measure pi, then there exists a unique, strongly stationary Markov chain that is ergodic. Okay, so that's important, because if we have a unique invariant measure for the transition kernel, we will have a Markov chain that is ergodic. So it will be possible to apply the strong law of large numbers. So what we will want to show is that the kernel K of our Markov chain for the abundance has a unique invariant measure. So I will go back to the model. So our abundance time series YT, we will assume that it is a Markov chain with a transition kernel. Okay, so remind you that it's probably the conditional law of YT conditionally to YT on S1. So the transition kernel will have a mean mu and an unknown dispersion parameter. And the mean ui will be written in that way. So it's the explanation of the vector of regressor beta I, sorry, times y. So in the reality, y will be yt, okay? But in a more general framework, it's just one. And it is possible to show that our kernel here satisfies a condition that is a Dublin's condition. And actually, for all y in E, so here is the simplex, and all event A on the sigma field calligraphic E, we have K of YA that is greater than a number eta, a scalar eta, times lambda A, where lambda is some measure on E. So why is it important? Actually, I will just maybe I will think that later, but is that if the kernel K satisfies the Dublin's condition, then we can show that it admits a unique invariant measure pi. Okay, so here, if I sum things up, we can show that our transition kernel for the model that is the Dirichlet kernel satisfies the Dublin's condition. And since it satisfies the Dublin's condition, there is a unique invariant probability measure pi. So, because it's a Markov chain, there is a unique, strongly stationary process YT of abundance with transition kernel K that is ergodic. Okay, so here we can assume that our model of abundance is actually ergodic. And it will guarantee us the strong consistency of the maximum likelihood estimate.
Maybe it can imply more strong consequences.
The fact that it is ergodic or the Dublin
condition this way, it means that you have irreducibility and periodicity of the Markov chain. And then you have exactly the condition of the Phoenixing condition.
That's yes, I believe you. That's not something I really know, but yeah, surely. Okay, so the Dublin's condition is actually
A very strong one.
yes, stronger than I imagined actually.
Yes, in fact, because you stay into a compact set, and this
Yeah.
is a very strong assumption.
Okay, so maybe if we have time, sometime we will prove that. So those are quite really general results, but maybe we will just show that our kernel satisfies this condition later. That could be a good idea. Okay, so because the process is ergodic, like I said, if we assume that it's ergodic and because it exists, the model parameters phi and the regressor vectors beta 1, beta 2, etc., they are estimated by the maximum of conditional likelihood, and it is strongly consistent, like I said just before. So with our Scandinavian birds data, we obtained those results. Okay, so it's quite difficult to interpret for now. Just an important one is the estimate of phi. Because here, remember that phi is a dispersion parameter. And last week I said that the higher phi is, the less variability we have actually in our model. Last week we had the opportunity to show that the higher phi is, the less variability there is, and it is quite strange, I think, that we have this value, because when we took a look at the time series with the previous graphic, maybe I will just show it very quickly. Yeah, it's enough. And you can see that there is some variability in the three species. Okay, here for Calcareus, there is a lot of variability. So I thought that it was quite strange to have such a high value of phi, because 171, it's really high, actually. But okay, maybe it's just because we calculated our estimates with only 38 values, because we have only 38 years. So maybe it's not very. Maybe we don't have enough data. Or maybe there is another explanation. We will see that later. But okay, just remind that that's quite strange to have such a high value for phi. And here, so this is really not a good graphic. I wanted to show it because I think somehow it can show how much a graph can be misleading sometimes. Because here it was just the first try. Said, okay, I have my model, I have my estimates. Maybe, like for the Var model, I can take the first true value and estimate the next value for my abundance of birds. Okay, so I take this value, I estimate the next one, and then at each step, I take the real value observed. For example, in 1980, I take the real value observed, and with my model, I compute the prediction for the year 1981, etc., etc. Okay, I make my predictions step by step. And what happens is that you have almost the dotted line that is equal to the full line, but we just have a lag of 1 year. Okay. So sometimes if you see that, and I know that I had some friends at first when I was a student that thought it was a very, very good graphics. Because you see the dotted lines, they are almost equal to the full line. So you say, okay, my previsions, they are nearly perfect. But it's not true. Because there are just predictions step by step. And you see there is just some kind of lag in my prediction, and that's all.
But these are one step ahead the prediction.
Sorry?
Is one step ahead the prediction.
So one step, at each time I take the true value,
Yeah,
the
so
true path
you
value.
go just one step ahead. So if you have YT, you predict YT plus 1.
Yes.
Correctly. So
Yes.
that's actually normal that you have this lag.
Yes. And here, actually, what is happening is that at each time, my prediction model does almost nothing. Because if there is no differences or almost no differences between besides the lag, it means that for my future prediction, for instance here, I just say, okay, so it's the same value as this year, and I just modify a little bit the abundance. And each time, this phenomenon. For example, here, for the red species, if I make this prediction here, what my model said, what my model did is that, maybe I just use the mouse. Okay, so here I'm looking at this part on the graph. And so it's 1970. So I want to predict the abundance in 1971. I say, okay, I take this value and it's almost the same. I don't move it. Maybe it will be slightly lower, but that's all. But in reality, there was a huge difference. Okay. And after that, okay, my model say, well, I take the true path value and I will just modify it very slightly, etc., etc. So there is a problem. You could say that it's a perfect fit, but not at all, because the model does nothing. It's just, okay, I take the path value and I make almost no modification, and I just predict the future value as the present value. So there is no interest in it. Okay, so why? I was wondering why my model does that. Well, it's because there is such a high value for phi. Because phi is really, 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 really high. Well, the model will always say that there is almost no difference between two successive years, because there is almost no variation. So maybe that, like I said, maybe there is a problem with my estimate, and actually the model is not entirely the correct one. But with some modifications, we can have a better model. The problem is that phi is too high, okay? And I said in my model that phi was assumed constant. Maybe phi is not constant at all. And the idea is, I will just stop sharing to write it on the board. Okay. Maybe the idea is to say that, well, the parameter phi is not constant. We will have some kind of regression with the link function. Maybe we have log of phi that is equal to gamma times scalar product between the vector gamma and the previous value of abundance, which is equivalent to have phi is equal to exponential product yt minus 1. Okay, so there is a link function that here I chose the log, the logarithm, because I think that changes something. Okay, the dispersion parameter is strictly positive. It's greater than 0, so I choose a log link function. And I can build a model where gamma here is a vector of regressors that is unknown, and I will try to estimate it. Actually, it does not change much in the model, so it is possible to make this assumption. And with this specification, the dispersion parameter will change at each time. Well, it will depend on the real value of the abundance. It's not something that is constant along the years. So I just decided to take this model. And here is what I obtained. And it's okay. So you will say that it's not good at all. Yeah, obviously, at some time it's completely absurd. But here, what I made is I just took the first value, and then I let my model make all the predictions. Means that it never used the true path values. I just take the original first value, okay? Then I make my predictions for 1965, and then for 1966, I just used the estimation of the year 1965, etc., etc. So all these predictions, they are calculated according to the previous estimation and not the previous real value. So it's quite interesting because here I actually made some predictions not with an horizon equal to 1. It's not step by step, but I just have the value for 1964, and I'm trying to make some predictions for the 38 next years. And as you can see, well, I think that the model is really, it's really good because you have somehow you have the good trends for the 3 values of abundance until I think it's 1984 or 1983, something like that. So during 20 years, my model was quite correct for the trends. Obviously, there are some big mistakes here, but still, the trend is quite correct. Okay, here, you can see that there was something quite strange with Capillarius. Okay, there was a huge increase for the red species in the beginning of the 70s. And the red species was even more numerous, yes, than the blue one. But for some reason, for some unknown reason, it declined. Okay. It declined maybe too fast. According to the model, the red species was supposed to decline later. But the trends are quite correct until 1982, 1983. And I would say that there was probably something quite strange in this period because, yes, there is a huge increase, well, not that huge, but a big increase for the green species big decrease for the wider one.
Sorry, William, what is the model that you are fitting there, that you are estimating there?
It's the same Dirichlet model, but the dispersion parameter here depends on the path value.
Okay.
In that way, it's not constant anymore.
Okay.
This is the only difference.
And how you estimated this, considering how many observations? Just the first?
How to estimate gamma? Or
Yes, to estimate gamma, so to estimate fit.
to estimate gamma, I just use all the data.
Okay.
And then when I want to, I compute phi with the value of gamma.
Okay.
But I never take the true value of y. I just replace y with the estimation.
With the fitting. Okay.
Yes.
So like you are making like H-stepized prediction. And this is why you have this situation after you lost the information of the data, and then the model
Yes.
go away.
Yes, and that is really normal to have some kind of behavior.
Yeah.
Because it's at some point it's really you have too much approximation.
Yeah.
And it's starting to explode here in green.
But I think that is not you have this behavior, but nothing is happened in the real world in the 1983. It's just that the model.
Maybe it's just maybe it's too much steps ahead. But well, I was quite surprised that for 20 years it was quite correct. And well, maybe I'm trying also something else because sometimes with a little bit of luck, I have.
After too many labs is unusable to make prediction.
Yeah.
It's going to have something that is totally unusable.
Yeah. Yeah, because even in the real world, there are so many things that can happen, and maybe it's not correct anymore. Okay, so here you have the predictions, but only with the first value. So I think it's quite. There are some improvements to make, but it's quite interesting. It's a quite interesting model, and I still have to prove because there are some demonstrations in the models I did not make yet with a non-constant parameter phi. But I think it works the same. Actually, if I make these specifications, I'm not sure that my model that the estimates will be consistent, but I think it works the same. I just have to check all the math behind, but I did not have the time. Not yet. I think it's okay. So after the predictions, there is one point of interest here. It's the interpretation of the parameters beta I. Because I don't know if you remember, but for the beta regression or Dirichlet regression in the static case, we said that there is an interpretation of beta I in terms of odds ratio. Okay, so it was measuring the evolution of the power balance between the different proportions. Here it's quite the same. So I just take again my birds in Scandinavia, and I will assume that between time t and t plus 1, the abundance will evolve according to this equation. So the first species will have an increase of c in a proportion, and the second species will decrease of c. So the last one does not move at all. And I will consider at time t, from just time t for now, the power balance between the two species. So I will take the mean of a species 1 divided by the mean of species 2 according to my model. Okay, I say so it's a power balance. If it is greater than 1, the first species is dominant. Otherwise, it's the second one. And if I want to see the evolution of this power balance, so I take the power balance at time t plus 1 divided by the power balance at time t. Well, it's quite easy to show that it is equal to exponential of c times this sum of coefficients with the beta regressor. So here is the first vector of regressor, if one is in parentheses. And the second vector of regressor with the 2 in parentheses. So once again, there is an interpretation for the parameters beta. And it's an interpretation in terms of power balance. Okay, if there is here an increase for the first population at the expense of the second species, the power balance will evolve in this way. So what can happen, for example, if the sum of the beta coefficient here is negative? Here, if it is negative, it means that the first species will actually decline later. There is something that is not good, because it will grow in the first instance, but maybe the second species will decline too much. And if the second species was a prey of the first one, the first species will then decline. Okay, because there are not enough preys in the system, in the ecosystem, for them to survive. I think that that can be interpreted that way. Okay, so I think it's all for that I wanted to present today. Maybe you have some questions. Maybe we can make some proofs. I talked about. There was a doubling condition, for example. I don't remember where it was. Sorry. Yes, that was it. I don't know if you have any questions about the model I presented today. I don't know what can we do because it's quite early, actually.
Can you back to the no, it was can you back to the graph when you make the one step ahead the predictions?
So the not good one.
This one.
Yes.
This one you was worried about the lag that you see in this, but this is perfectly common.
Yes, but what I was unhappy with is that we have really almost no variation.
Yeah, because
okay. For example, with the var fit, it's not that identical.
no.
No. With the var model, you still have some. I'm sorry. You still have some variation sometimes. Okay, you have some lag, but you have some lag, but it's not the exact same curve.
Okay.
And what is suspicious, because the model is not the right one.
It takes just the value of
yes.
before, basically.
Basically, it takes just the value before.
Yes.
And it just translates it
exactly
to the right. So obviously, it's not exactly the same value, but there is almost no modifications made.
Yeah.
So when I see this, I say to myself, okay, there is something wrong.
This what is which model is it? This one?
It's a direct model, but the parameter of dispersion phi is assumed constant. So we do not make.
It's like it does not learn information from the data.
Yes, for the dispersion, yes.
But
there are just the beta parameters that are learned, but for dispersion, no.
But sometimes it's happened that the ARMA make this stuff also.
Yeah, probably because I'm not really used to work with ARMA models.
Okay.
I saw some fitted graphs that looked a lot like this one, but each time I see something like that, I think it's quite suspicious.
And did you evaluate the goodness of fitness between this one and the other one?
No, I actually did not have for the presentation. I did not have the time to make it. It would be good.
Yeah, but you can do it just to see if take the difference between the fitting of the.
Yes.
You take the
Well, I think it's quite high because
you take the blue with the dashed line. You take the difference between this line, and you evaluate the mean of the square.
yeah, but
Difference.
yes, just yes, like an MSc.
Yes.
But I did not make it because I thought it was not a good fit somehow. But I think it's quite the MSc should be really high because you have some enormous differences. For example, many times when the prediction is here, actually in the middle of the graph here, the true value is really below. I think that the MSc, it seems like the curves are really close one to another, but I think the MSc will explode.
You can also try to see what happens if you take a larger horizon. For instance, instead of take one step ahead, you make.
Actually, I made it with a larger horizon. Maybe just because I will just make one small graph by hand. If you take a bigger horizon, what is happening is that you have almost, like I said, you have. For example, the first species, it made something like that for the prediction. For the second one was something like that. So there is really, really smooth. And for the third one, it was just a line.
Which horizon was this one?
I don't remember. I'm sorry, I don't remember.
But very, very large, like.
Yes, it was large.
You should try with 3 or 5.
Maybe 3 or 5 would be better, but yes, it gave something really smooth.
No, it's normal. It is smooth.
And yes, it's this is something that I expected, and it's also because you have a parameter phi that is really high, so almost no variability. It does not move. And yes, I think it's really interesting to have the parameter phi that is evolving. It changes a lot of things.
But you can estimate it directly with the maximum light with the parameter phi. It appeared and yeah.
Well, here I estimated when because you can estimate it directly if it is supposed constant.
Yeah, but you can, for instance, you can consider the sample like you do for prediction, and each prediction you estimate the phi based on this subsample. In this case, you have like a time varying parameter.
Yeah, maybe it could be. Maybe I don't know what would be the consistency or the asymptotic distribution of such an estimator. But maybe it's good, but I don't know.
Well, I think it's the same. It's the same like this one. You just consider a small sample. But if the asymptotic theory is the same for all the samples, no? Yes. Why should be not? You can also estimate all the beta with this way. Yeah.
Yeah, maybe. I don't know.
It would be nice to try other data.
Yes. Actually, sometimes I spent hours looking for nice data sets. And it's quite difficult because sometimes you have good data sets, but only on a duration of 2 or 3 years. So okay,
with this so small data set is a mess.
yeah, because it's normal because here it's in the lecture notes I put the reference of the data set, and it was really I think it's a Swedish
Anyway,
biologist.
you can run in your R, then time series library, and look to the Hidman time series library. There is a section of ecology where there are you see this data set.
But this one or
Hidman time series library. You know this.
okay, I will take a look at it.
Yeah.
And you have several time
download
series
directly on R.
Okay. And there are multiple time series data sets?
No, I think are univariate time series, but you can put put it together to construct.
Yeah, maybe.
Yeah.
During my my internship, when I worked about this model, obviously I also made some simulations to see how the estimators would behave. And even when you build the time series with the directly transition kernel, the estimators were quite slow to converge to the true value. So that is something that we have to work upon.
What you don't talk about the initial condition of the parameter, how you solve this?
I do not talk about it because that is still an issue that I have.
Okay.
Actually, when you want to compute the maximum likelihood estimation, the first the starting values of the optimization algorithm can change a lot of things.
Yeah.
And sometimes, a lot of times, actually, the method does not converge and the optimization fails. And this is something that I still don't know how to resolve.
Well, a trick that usually used in this case, for instance, you take plural, you have your dimension of your vector of initial condition. You draw from a uniform distribution like 10,000 of this vector. Then you evaluate this inside your likelihood function. You take the one that maximizes your likelihood function without the
and you take this as
without the quasi-Newton estimator, and then you take last initial condition.
Yeah, that could be.
Maybe it's you choose the one that is able to maximize better your likelihood.
Yes, this is something I will try this evening, I think. Yes, that's
I do like this. It works.
Yeah, I think it's quite clever.
Or we do like with dice because sometimes like an app you have just to change a bit.
Maybe it's a good idea even to suggest to run some simulation to the students to see what they can do. If someone is interested, maybe it would be a good idea.
You mean to ask to the students if they want to run some simulations of this model?
Yes, I think it's a good idea.
Yeah. So you want to make a simulation of the time series with the direct model? Yes, it can be a nice work. So I do not understand. Do you want them to do it?
Yes, maybe.
Yeah.
Do you think it's possible?
Yes, this is really possible. To because you are used to work with the software R?
No?
Python, maybe?
Vous ne travaillez pas du tout avec R?
Ouais.
C'est le même Python R.
En Python, maybe if you. Mais ok. Non, mais sinon. Ça peut être au moins l'idée, mais c'est. Ouais. En R, c'est facile. Il y a beaucoup de librairies. En Python, je sais pas trop, un peu moins. Mais je pense que ça doit être pas trop compliqué non plus.
Tu vas faire la
Transition.
pour la condition des deux billes.
On peut parler de la condition de Deaubin.
C'est bien.
Du coup, okay, but maybe we'll stop sharing. Maybe just so we try to prove this fact. So yeah, it's just a definition of the Dublin's condition, and we can prove that our kernel K satisfies this Dublin's condition. Okay, so I will just stop sharing this. Okay, I don't know if I will have enough room here.
Peut-être on peut même fermer l'écran.
Bah, je pense que ce serait mieux de remonter ça.
Oui.
Ouais. Ça va prendre un petit peu de place.
Du coup, oui.
Okay, so it's not really complicated, but it's it needs some space.
Du coup, on arrête de partager l'écran.
Oui, il faut en fait, surtout éteindre.
Oui,
Il faut surtout que j'éteigne le projecteur, et c'est surtout ça qui est obligé de
d'accord.
Okay, so here what we want to show. Okay, so we just use this board because it's just recorded here. We want to show that for all A, so here it's an event on the simplex, and for all Y in the simplex, we have the Dublin's condition that is satisfied. Okay, for some constant parameter theta and for some measure lambda. Just recall that the kernel K here follows the Dirichlet distribution. Okay, with dispersion phi, it is constant. Now we will just assume it is constant, and mean. So mu I is equal to exponential I divided by I1 plus okay. So K, this is this transition kernel. Okay, for I between 1 and d minus 1. For I is equal to d, it's just 1 minus the sum of all this formula. The first thing that we can show, actually, is that there exists for all I between 1 and d, there exists some positive constant mi, little m, and big M I, such that we actually have exactly it's What did I want? Because mu I depends on what? Okay, so we can show this first statement. It will be useful later. First, for big MI, you can take MI is equal to 5 because all the mu I of Y, they are included in the interval 0, 1. So it's quite easy to take just MI equal to 5 for every I, and it's okay. For the little m, so we'll consider J 1 and D minus 1. And you can observe that we have the exponential of beta j scalar y is smaller than the exponential of the L1 norm of the vector beta j. Because don't forget that y is an element of the simplex, so all the components of y are between 0 and 1, and the sum is equal to 1. So here, if you write the scalar product, you will see that you will just have all the components of the vector beta j, so it will be smaller than the L1 norm of the vector beta j. However, another element with the Cauchy-Schwarz inequality, you can also show that beta I scalar y is bounded between the L2 norm of beta I and minus beta, the L2 norm of beta I. It's norm in L2. Okay, why is that? Because the L2 norm of the vector y is smaller than 1, because we will still have elements in the simplex. Okay. Space now. By equivalence of the norms, also exists use scale, maybe it's not right. A constant C that is strictly positive, independent from I and Y. What is that? You have the L2 norm minus C L2 norm of beta I. Encore it one. Of sorry, I'm just a little bit lost in my formula. C'est vrai. Oui, oui, oui. C'est vrai, mais je suis perdu dans ce que je voulais vous montrer après. Quand on perd le fil après. No, it's not in the correct order. I wanted to write it. Wrote something that is a mess. No. I will just erase it because this is not the correct formula I wanted to show. Sorry, so here I have okay. So this I already wrote it on the board. Okay, okay. That's strange. I think that I don't need this equivalence of norms. I don't know why I wrote it here. Better than this. Yes, I don't need. I think I don't need this equivalence of norms actually. Okay, so I do not know what I wrote here, but this is something not useful. I can write the equality straight away, just with this with Cauchy-Schwarz inequality. Okay. Write it down. I have phi of nu I y. It's just phi exponential. Okay. This is correct. This is greater than phi exponential of minus the norm beta I L2 norm. Okay. Because of the Cauchy-Schwarz inequality. Okay, you have this scalar product that is greater than this L2 norm. By 1 plus the sum y. But we said that the exponential of a beta j scalar y is smaller than the exponential of the L1 norm of beta j. So because it's on in the denominator, this is greater than I times exponential minus the norm of I by 1 plus the sum of the exponential of the L1 norm of vector beta j. That's the L1 norm. Okay, so I can denote this little mi. And for this was for I between d minus 1, and for I is equal to d, it's quite easy. Because for I equal to d, 5 of mu d times mu d of y is just pi divided by 1 plus the sum. So this is greater than pi divided by 1 plus the sum of exponential L1 norm of beta j. Okay, so this is our parameter little n d. Okay, sorry, there was just something really useless in my notes. So it's more easy this way. So what we showed here is that for all I, there are these two constant mi, little mi and big mi, so that we have this equality all y in the simplex. Okay, so this is a preliminary result that will be useful next for the Dublin's condition. Yeah. Because with the Dirichlet distribution, just write it here, the density is equal to gamma of phi divided by gamma phi times mu1 times gamma phi multiplied by the product is equal 1 to d of which one would I choose? It's I at the power phi I minus 1. Okay, so for our Dublin's condition, we will want, we have for the transition kernel, we will have a probability measure with this kind of density function. And what we want to do is to find some lower bound for this function. Yeah. So if you take any I between 1 and d, and you want to estimate or to find some bounds to gamma of phi ui, and this is quite complex. If you take the gamma function, so it is the integral between 1 and 0 and between 0, sorry, and plus infinity of exponential minus t by t. You can split this integral between 0 and 1 plus infinity. And it is quite easy with the result we showed, we proved before, to have some bound. And to say that it is smaller. Yeah. So if t is between 0 and 1, yeah, it will be slower. T at the power little m I minus 1. Okay, because t is between 0 and 1. And between 1 and plus infinity, we take the upper bound of phi times ui. Okay. So here it does not depend anymore on y. And this is obviously smaller than yes, this notation, gamma of small m I plus gamma of big M I. Never know how to draw them. I will denote this sum. I don't know. Sine I. I'm not really good with those letters. For example, so there is an upper bound for gamma of phi times ui. So here I will have on the for the denominator a lower bound. It will be quite easy. So if I take my transition kernel, this K of Y and A. So because it's a Dirichlet distribution, it's an indicator of A of Y1 or X1. Integrate over my variable. X is just my integration variable here. Multiplied by gamma phi. Just Y constant times the product of the xi at the power I 1. And the goal is to find something that is lower, some kind of lower bound for this kernel, for this quantity. So all the gamma of phi nu I, we will use the psi I for the lower bound. It's greater than the same indicatrix, same index function, sorry, times gamma phi divided by psi 1 times psi d. And for the product of all the xi, well, all the xi are between 0 and 1. So the xi at the power phi times nu I, it is greater than xi at the power big M I. X1. Okay, so here it does not depend anymore on variable y. So it's almost a win. Because here we will find in the Dublin's condition, you have to find a constant eta and a measure lambda. You almost have your measure lambda because you almost have a Dirichlet measure here. And the constant eta will be a constant with all the gamma phi and all the psi I, psi 1, psi 2, up to psi. So here actually, this is the same thing as eta times lambda A, where eta is just the constant gamma phi times gamma of big M1 to gamma of big M D divided by the product of the psi I times gamma of the sum of the mi. And lambda is actually the directed distribution, but with parameters just m1, m2, etc. up to md. Okay. Because here we almost have, you can see in the product, you almost have a directed distribution with parameter m1, m2, etc. up to some multiplicative constant. So we just have to add some terms in the equation to really obtain the directed distribution, and it's okay. So for our transition kernel, which was a directed transition kernel, the Dublin's condition is satisfied. And what is quite, I think, from a mathematical point of view, which is quite interesting, is that the measure in the Dublin's condition is also a directed distribution. So there is, I don't know how we can say that in mathematics, but there is some kind of stability somehow in this, with this distribution. Because here the distribution in the lower bound is also a directed distribution. So as you see, there is nothing. I was quite lost at some moment because there was something that was useless in my notes, but there is not a big majoration, not big result. It's quite easy to show that Dublin's condition is satisfied. Then Dublin's condition guarantees the existence and uniqueness of an invariant probability measure, which ensures the ergodicity of the process.
You have can you recall the proof of this point? How do you
The existence and uniqueness of
yes.
I just it's in all the notes. It's longer.
Okay.
I can just write the big ideas, maybe.
So do you prove that the Markov kernel is constructive?
Yes, but this yes, there is it's constructive with total variation distance.
Yes.
I don't know if you know.
Maybe
the
this
total
would
variation.
be a good idea of a result to prove. In fact, there is a lemma
Yes.
which proves, which is Ueno's lemma. Do you prove it?
So, sorry, the name?
There is a lemma which names is Ueno, the Japanese guy.
Okay, maybe it's this lemma, but I do not know if it's this
Okay,
name.
but maybe this would be a good idea to suggest a real to redact this proof. It would be a very good example, I think.
Like an exam question?
Yes, exactly.
Yes,
So,
it's not that obvious. It's because I think that there are, with this proof there are a lot of hidden points that seem obvious at the first sight, but you have to take care.
yes, I agree.
Because some things are not that obvious and easy as we can think. But yes, this could be a good question. If I had two exam questions, it would be maybe this one and way more, way easier one.
Maybe I stop the
Yes.
record.
Be show